So please note down, it is from 25th afternoon, suppose say 3 p.m. to 6 p.m. Okay. Although it will not be required that much, but then we just block the time, say 3 p.m. to 6 p.m. Okay. And the exam, I have got the permission from everybody that exam will be online. So now all of you are perhaps comfortable with this code tantra. Am I correct? Who is the representative of the class? Who is the representative? Class representative? Hello?
Yes.
Who is that?
Siddhant.
Siddhant. Okay.
Yes.
So all of you are comfortable with code tantra?
Yes, sir.
Huh?
Yes, sir.
So can we have a mock, maybe by this weekend, can we have a mock with all of us? Like, how are we going to execute our end-sem examination? Can you arrange for it?
Okay, sir.
You coordinate with Vinod. Okay. Essentially, the exam will be open book, as I suggested, right? Open book, open notes, open resources. Okay. So I'm going to frame some very interesting heat transfer problems, process engineering problems. And in those process engineering problems will be distributed to all of you. And there is a possibility that, some of you will have the same question to answer, right? But the credit to those who are going to give me the unique solution. So I will be marking them, those who have done the solutions in a more unique manner, rather than, coming up with a kind of, a routine solution. So that will decide the grade. That will decide the gradation of the numbers. Okay. That will decide the gradation of the numbers. Okay. So is it clear, Siddhant, to all of you? Yeah, so we will do a mock on maybe you decide based on your convenience. I believe 17th tomorrow we have a class and 17th we have a class. So we should not collide with these 2 dates. So maybe 18th is a good time. 18th morning, Saturday morning, if we can sit down for half an hour or 1 hour to figure out how exactly we are going to manage the examination. As such, I don't want to be strict with any one of you, but then the diktat that has come from the top is that we have to have a proctored exam. That is the only limitation that academic section has given to me, that this exam should be a proctored exam. That means all of you should be visible to me. I should give you a stipulated time. I was actually planning to give you 24-hour take-home exam, right? But then I could have pursued a little bit more. They would have agreed. But then I did not do that, because they are into so many, problems are coming due to COVID. So they are really stressed. So I just thought that, okay, let us do in 2 hours only. So, and then, we will come in this particular forum, and then I'll test your creativity in 2 hours time. Is that fine, Siddhant, with all of you?
Yes.
So I'm going to say, suppose 90 students are there. I'm going to make about 10 to 12 questions, and then I'm going to circulate it randomly to all of you. And then you answer as per your imagination in 2 hours time, come up with a solution, and we do a proctored examination, and we collect everything online. So at the end of so we keep 15 minutes for the distribution in the beginning, then 2 hours of exam and 15 minutes at the end to collect the papers online, right? So in that process we finish. Of course, there will be some issues. Some has issues with their bandwidth, internet connectivity, and all these things that we will be very, very considerate. Okay, in no way our intention, at least my intention, is not to penalize you. But then, of course, I will be very, very limit to those who will try to really, copy these, that, I just don't like it. If I get a iota of hint of that, whatever you are writing is not your effort, somebody else's effort, I will be like, I'm very severe in those regards, right? I can give O up to F, even without thinking about, if I see that there is plagiarism issues, and then there is, say, in terms of ethics and values, I just don't compromise. So I'll be immediately going for F and all. Okay. So be careful about that. But you are doing honestly, you are giving examinations and all. I am all with you. I just want to make sure that all of you come, read the lecture notes. Okay, use the lecture notes to give me the answers, and I'll be absolutely happy to like, give you as much marks as possible, right? That's the whole spirit. That's the way. I don't want to be a chore. I don't want to play a chore police game here, right? That's not my job. I'm a professor, you are a student, and we should respect each other in order to make sure that, and it has, enough. It has happened. Like I have seen, people are doing like, different types of malpractices, and enough. I just don't want to get into that mess. If I get an iota of hint that, it is in that level, I'm just going to be as severe as possible, right? But then, 99% students, I know that, they generally like, I'm taking exams for so many years, this open book and all. I don't see like, there is any type of copying and all in the exams that I have taken. And, whatever rule I lay down, you follow, finish it once for all without any problem in the future. Is that okay, Siddhant?
Yes, sir.
Yeah, please convey to all your friends in the class likewise, and let us arrange a mock on 18th. Okay, how we are going to, and you tell me, like, how am I going to distribute the question paper? How are you going to help me in collecting them, right? Without getting into like, these frauds and all. Okay. Now, now and then, I evaluate and let us keep it simple. More these parameters come, it becomes very, very complicated, and nobody knows what is right, what is wrong then. And let us finish this activity, because our main objective is to learn, and that's where we should focus. Okay. Anybody has any questions in this regard apart from Siddhant?
Sir.
Yeah.
So it is an open book exam or closed?
Yes.
Open book.
You can look at the lecture notes in order to, you can look at the lecture notes, you can look at the books, you can look at the internet materials in order to come up with a solution. Is that fine with you?
Okay, sir. Thank you, sir.
But then I don't expect you copy from somewhere, right? Moment I see there is a hint of like, you are copying from some book, this, that, I am going to frame the questions which will be very unique. You will not find in the books, copies, and anywhere, right? So make sure that, these will be all real life problems, and, they will require a lot of imagination to solve the problem. Most importantly, there is no solution. I also do not know the solution, right? So I will be looking for solutions, and with the fundamentals that we are studying here, right? So of course, each one of you should really think in a very unique manner, and then, give me a solution, rather than I see like, two are giving me the same solution. Then, both are zero, or maybe very similar, then both are zero. I am not going to really consider a single case there. Okay. Yeah. Any other question you have?
Yes, sir. Yes. Last class you had said that we can discuss like with like you like we can discuss with you also, like whatever things are there.
Yes. I will give you my mobile number, but then, in 2 hours time, see, I was planning 24 hours. I wrote that way, that it will be a take-home 24/7 exam. But then they said that, it is not allowed. So now I have to restrict it to 2 hours and a proctored exam, right? That's the only restrictions that I have received from the academic section. That's why I say that everything I will finalize on Monday, right? So the only difference is that my phone number will be available with you. So you can discuss with me, you can call me and discuss with me. I'll be online available with you. Okay.
So how many questions will be there?
Pardon me, can you repeat?
How many questions will be there?
Template will be one question each for everybody, but in questions there will be sub questions perhaps. Okay.
Okay.
Also, sir, like
so you have to be very alert and very very methodical and very prompt if you really want to do something in 2 hours. The question will be set in that manner. So just I just give you simple examples. Say suppose you take a matchbox and you just take a matchstick, and then you have a friction and you burn it, right? So I may just tell you that how exactly this friction, what is the force that you are putting in, and then how. See, I don't want radiation here, because radiation I have not taught. So convection, conduction will be done, at least like the laminar part. So use the principle of conduction and convection so that this work done is getting converted into heat. I don't think any internet material, any book will give you this sort of things. So I just like to see how exactly you are able to work on the surface of the matchbox, and then how are you using 1D 2D conduction equations, and then how the air is coming in as the heat is generated, and from there you're making the energy balance. So in 2 hours time, you really have to be very alert in order to really get a solution to that. Is it clear? I mean, what type of thing that you are going to face in the mid-sem exam? Yeah, Mohit.
Yes,
Yeah,
sir. No.
Akshat, Pahle Akshat. Yeah, Akshat.
Yes, sir. Sir, I was asking that we will be required to scan and upload the answers, right? So in Code Tantra,
Bolo.
so in Code Tantra last time, there was one exam in which we were required to scan and upload in Code Tantra only, and it was a bit problematic. Many
You take a
people.
mobile image, upload, I don't mind. Okay. Whatever you do, you write, and then, I don't want you to, that we can decide on Saturday how we are going to upload. Okay.
Okay, sir.
Right. If you do on a handwritten copy in front of me, then you take a snap and then, you upload directly. I don't mind that. The only thing that you have to ensure, that you have done that at that time. After you have received the question, you have thought on the question, you have done on a piece of paper, and you have communicated to me. Keep it simple.
Okay.
I don't want scan these, that, don't bring in all those things. I just want to see what you are to say. Suppose if there was an exam in the class and I have given you an exam paper, you have written something and I would have taken, right? If we can just do that in whichever possible way with this online platform, I'll be happy.
Okay, sir.
Without cheating anything, without taking somebody else's images and all these things. Okay. That we figure out on 18th. Okay. Yeah. Mohit.
Yes, sir. Sir, I was just telling that the new students who have joined, changed their branch to CL, they still haven't been added to the Teams group.
Can you please help us in identifying?
Sir, myself.
Can you please help?
Yes, sir. There are 5 students.
Okay, can you please email? Can you please email to Vinod with the emails? So they will be added immediately. Okay.
Okay, sir. With all their 5 students' emails, right?
Email and name. Okay.
Okay, sir. Yes, sir. And also one more thing, sir. Will the questions be solvable in 2 hours?
No. It's an open-ended problem, right? So don't expect, I'm looking for a number. Anyway, I'm testing those things in your Viva, right? So I'm not going to give you something very definite. So you have to really be careful, lead all the lectures, the chapters. You have to be ready, and it will be from the syllabus only.
Okay, sir. Yes, sir.
Okay, it's an open-ended. You will enjoy. Generally, I have seen people have enjoyed this type of thing because this is what real engineering is all about, right? If you know the solution, then there is no engineering. So yes, I just want people to get that taste during the, this is what is missing in most of the teaching practices. You are always given a problem which has a solution. Most of the real life problems do not have solution.
That's true.
You have to find out a solution, right? And you have to use all your wisdom, knowledge in order to find out the solution. And that's where the fun is. That's where the fun of invention and discovery is. That nobody has this. You cannot imagine you can really do that. And you see, people have congratulated me last time when I took. I think there were how many, about 20 problems were there. All were very different. So students just called me after the examination and they were so happy after discovering that they can do that. Right? It is, you have to frame it. You have to have this is the stepping stone. One thing is that you read and from there you develop a solution. That's more of a kind of tailor-made stereotype that doesn't help much in your practical life. In practical life, problems are very different. They will come in a very different form, and you have to really use your wisdom in order to. Intelligence doesn't help at the formative stage, by the way. Intelligence helps there. Formative stage hard work helps because you gather the knowledge with your hard work. But then later on, with the use of the knowledge, if you bring in your intelligence into picture, then you solve the problem. Say suppose I may tell that this Brahmaputra reservoir that is there in front of IIT, right? Say suppose there is sun beating taking place, right? Say suppose how will you model the variation in the water temperature, surface temperature with respect to the entire day? And then just don't use radiation. You consider sun as a heat source, and from there it's a surrounding and system, and then do an energy balance to just I just want to know what is the surface temperature of the water. What is your model? Right. So you will not find all these things in the internet and all. You have to really assume that this is a 3D reservoir. It's a one-dimensional reservoir, and then there is a heat source at the top. So Q is coming in. So whatever you have read in the book, you have to really improvise on that. And then you do energy balance and then come up with the heat transfer, conduction, convection. So there'll be recirculations, conduction, heat transfer coefficient. There'll be air blowing from the top. So as you bring in the more realistic parameters, you will see these are all being taught in the class, and it is solving a realistic problem.
And maybe the answers will also surprise us a bit. Like it may be
Yes.
close to what we expect.
Yes, there is no model answer. There is no model answer to. Yes, that is true. Okay.
Yes, sir. Sure, sir.
Yeah. And you have to leave to my judgment that whether you have done well or not. Okay. For the time being. I mean, of course, I can be wrong. But for the time being, you have to leave to my judgment. How have you done? You try and get that estimate. That will be my request. Rather than getting into this, 2-number, 3-number, plus minus. It is very, very important that you need to know whether you are A grade, B grade at this stage. How was your attempt in my eyes? Because that's where the role of instructor comes into. And sometimes you will be disappointed, but please accept my judgment there. That will be my request to you. Okay.
Yes, sir. Sure, sir.
Okay, then. So if any other question is there. If not, so let us start today's lecture. And just to make it more interesting, last class, who asked the questions about turbulence in the last class, by the way? Can you please, tell me what is your name? Who asked the questions?
Sir Neeru.
So I'm sorry, there was an internet, cut off in the middle. I'm extremely sorry. So I was just asking the question that who was the student who asked the question last? Am I audible to everybody?
Yes, sir.
Yeah, who was the student who asked the questions quickly?
Sir Neeru.
Niru, yes. So thank you for your question. And today, we are going to really see how, this, turbulence, that sets in and how exactly we really study this part, right? So a few parts, will be added to the lectures, and then, sorry, from there, we'll be taking up the whole thing. So now we are very much, very much comfortable with the terminology that is called laminar region, where the fluid flow moves like a pack of cards, and then transition where we see some sort of recirculation that starts, and turbulent means it's a chaotic flow with a laminar sublayer and a transitional sublayer, right? In the free streams, it's extremely chaotic, whereas you have a sublayer where it is recirculatory, but there is somewhat flow patterns are there, and then there is a sublayer, right? And these are all decided by the Reynolds number, which is inertia to viscous force. In the laminar domain, the viscous forces are dominant, whereas in the turbulent domain, the inertial forces are dominant, right? The diffusion of this lamella, that has been decided by the parameter called kinematic viscosity, whereas the measure of the friction, that means the drag that is associated with the flow, that has been decided by the parameter called the dynamic viscosity. So Reynolds number is a measure of what? It's a measure of whether the flow is turbulent or laminar. So in a laminar flow, we saw that the flow can be a plug flow to developing flow to fully developed, whereas in a fully developed turbulent flow, we see that there is a turbulent flow core and there is a laminar sublayer. And then we understood that these are the situations for an incompressible flow. For an invisive flow where the viscosity is absent, we can apply Bernoulli's equation. And you also have a compressible flow, high-speed flow. In that situation, you need to really take care of the stagnation properties. And stagnation properties are doing nothing. What? It is taking into account the variations in the density. So we did derive the Bernoulli's equation just with the assumptions, 5 assumptions: steady state, frictionless, irrotational, and then what are the other 2 assumptions that we had? Streamlined flow, right? Streamlined flow, irrotational, frictionless, steady state, and then we had another assumption. So total 5, assumptions are there. When you really develop into it should be a streamlined flow, it will be a steady state flow, it will be a frictional flow, and it will be an irrotational flow, right? So with that, we figured out the Bernoulli's layer. And then, the question came up that, how exactly you are going to tackle a turbulent flow, because suppose if there is a turbulent flow, and then, if I put a probe here, I'm just going to observe a kind of fluctuation in velocity like this. So what we decided that we are going to talk about a mean flow that is U bar, and then there is a fluctuating flow that is U dash, right? And then there is a V bar and V dash. But then, say you will find that over a period of time, if you just, take a summation of this del U by del T, that means, what am I trying to say? That over a period of time, say suppose over a period of time, I want to really know that how this, this U dot, see del U by del dot, right? So del U dot by del T over a period of time, say suppose 0 to T, right? Into dt. How does this change it, right? This you will find out to be, for a turbulent flow, for an isotropic turbulent flow, this you find out to be 0. That means, there is a mean flow, there is a fluctuating flow, and that fluctuating part is as much as towards the higher side as much as there towards the lower side, right? So, this is the advantage of the turbulent flow in terms of like, modeling it in terms of mean flow and the fluctuating flow. I'm going to come in a more detail now on that. So these were the stagnation properties that we derived. Now, this is the classic example of a problem that we start with. These are called the Bluff body problems. Okay. So what are these problems? These are called the Bluff body problems. Okay. What is that? What am I assuming here? I'm assuming that there is a sphere. And then there is a flow. It can be water, air, anything. This is a solid surface, right? It can be a cylinder also, infinite cylinder, okay, on which we are forcing air to flow or say water to flow. Now, when the Reynolds number is very small, that means when the friction forces are very high and the inertial forces are very low, then this type of flow is called a creeping flow. What is the creeping flow? The flow is approaching, then this is climbing up, then this is going down, and then this is going out like this. So in the downstream and upstream, the flow is literally plug flow. But then when the obstacle is there, it is just climbing and coming down. This type of flow is called what? This type of flow is called the creeping flow. This is called the creeping flow rate, right? Now, if you increase the flow rate a little bit, what will happen? At a particular point, this flow will separate and they will create steady recirculation. So these are all steady vortices that will generate. This flow will separate and will go out like that. There'll be a stagnant fluid. But since this flow is going like that, this stagnant fluid will not remain stagnant. Why? Because there is an exchange of inertia from this side to this stagnant fluid, which will create these two vortices, which are counter-rotating vortices, right? And this will create a steady recirculatory zone at the back end. This is at moderate Reynolds number, but again, this flow is not a turbulent flow. This is a laminar flow, right? Now, if you even increase the Reynolds number, you will encounter a very interesting phenomena that this separation point will start oscillating. Both of them will start oscillating. So you may find this separation point is oscillating between a period like this, and this separation point will also be oscillating. That means it will be going this. So in one cycle, when it is here, this will push back. So there will be some flow pattern created, whereas in other cycle, this will be pushed back. And in that process, there will be a vortex street that will be created. That is called the von Karman vortex street. That is at the downstream of the channel. Right? Now, in these situations also, the flow is not turbulent, but this type of flow is called, they are called the coherent flow. These are called the coherent flow. That means there is some sort of flow pattern. There is some sort of flow pattern. Even then it's a laminar flow, there is some sort of flow pattern which are called the coherent flow patterns, right? Now, if you increase the Reynolds number further, then what will happen? This coherent flow only will become an unsteady flow at the backside of this Bluff body, which is called the turbulent wake region. So these recirculations will start interfering. So there is a flow pattern associated with this in the von Karman vortex street. But then, if you increase the shedding frequency too high, what will happen? They will start interfering with each other to create a kind of a very chaotic flow at the backside of the Bluff body to create the turbulent wakes. Whereas if you increase the Reynolds number even further, what will happen? This separation point, because of this inertia, this separation point will again push back towards the downstream. So you will see that this zone will become very small, but then this part will become extremely chaotic. The fluctuations part will be very, 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 very high. So this is a typical situation of a laminar to turbulent transition, right? And you can very easily estimate that here on top of this, you will have a situation like a kind of laminar boundary layer, whereas this type of situation you will experience a turbulent boundary layer you will experience in this sort of situation. It's a real life situation. I'm talking about a cylinder. Why? Because if this cylinder is converted to an aerofoil shape, this aerofoil shape can be this can be the shape of the aircraft with the tail and the wings here, or this can be the shape of the cross section of the air wings, which are called the streamlined shapes. What is a streamlined shape? Say suppose from this sphere you have converted to a kind of an aerofoil shape like this, right? Now what is happening? So you may see that these 2 points are typically called the stagnation points, where the velocity is 0. So this is a stagnation point. This is a stagnation point. This is a stagnation point. Sorry, this is a stagnation point. This is a stagnation point. These are the separation points, right? So similarly, at the nose of the aerofoil shape, you have a stagnation point. Now, slowly you will see the laminar boundary layer will grow, and as it goes towards the downstream, the turbulent boundary layer grow, and then towards the tail, there will be a separation and viscous fluid. Now, why are you doing the model like this? Because these weights are, say, suppose you are, this is the work that you are putting into the system, right? If this is a system, this is the amount of work that you are putting in. This inertia is your expense. It is going from your pocket. Now you want to make use of this particular work into something, you want to encash this particular investment. So in a turbulent flow, which is at the backside, where these recirculations, they are essentially the work that you have invested, it is generated from that. So if you have a turbulent boundary layer, then you have an issue in terms of wastage, too much of wastage. So a streamlined shape, you may see that, see, you have to understand that you cannot avoid even friction for a aircraft. Why? Because the aircraft is lifting from the ground. It's only because of friction. If there is no friction, you do not have any lift. Since there is friction, there is drag. Since there is drag, there is lift. And since there is lift, you are basically able to lift the aeroplane with so many passengers, with so much of weight, say upward. Now, in that sort of situation, so friction is necessary. Friction has to be there. Otherwise, you are not able to lift them. Now, then, how exactly you manage your expenses. So you have to minimize the friction. So how are we minimizing the friction? So if you look from here to there, laminar boundary layer, you end up that anyway you have to lose, in order to generate that drag. So, we will try to make sure this laminar boundary layer is extending as much as possible, which will helping in drag and lift. Whereas you have to minimize the turbulent boundary layer and the wake zone. This is the main loss. Even turbulent boundary layer is not the main loss, because in this situation you do a lot of heat transfer activities. So you may see that as you are going downstream of the channel, wherever there is a turbulent boundary layer, you try to put the engines, okay, where you have a turbulent boundary layer and you do a lot of cooling activities in order to make sure that that your aircraft is not getting, your engines are not getting heated up beyond a particular point. And then the streamlined shape is doing what? The separation zone, trying to the streamline this tail and all, is trying to make the separation zone as small as possible, because there you are wasting a lot of work which is coming like this. Although this is an inverse problem, right? Essentially this airfoil is moving and then this air is stationary. But you can look at this as a kind of problem, like there is a free stream flow and then there is a wing, and in that you have laminar turbulent boundary layer at the viscous wake. So this is the theoretical way of understanding things, whereas this is the realistic picture. This is what happens in a this is what happens in a real life situation in an aircraft in a airfoil shape. So laminar boundary layer, transitional boundary layer, turbulent boundary layer, and viscous wake. Question is that how do we really model, right? So one very interesting fact of this, you will understand that. Say suppose if you look at the drag of all these happenings, right? So this is your drag coefficient, and this you are varying with respect to this. Maybe say suppose this is the Reynolds number, right? So as you increase the flow rate, you will find the drag will reduce as it is becoming turbulent, right? And this particular point you will see in the turbulence, if I look at the turbulent domain, in the turbulent domain, you will find this is the place where your drag will be maximum. But in this sort of situation, you will find that there will be a sudden reduction in drag. Why? Because because it has pushed it towards this domain, so that you come here. So typically you will find that for aircrafts, for car, for different types of automobile devices, you have an optimal velocity. Say suppose if you are driving a car, people will tell you that if you drive at 40 to 50 kilometers per hour, at that your fuel efficiency will be maximum. Why? Because at that regime, your drag will be minimum. So that's why you want to change the gear and get into the fifth gear as soon as possible and get into 50, 60 kilometers per hour. Right? In that situation, your efficiency, your fuel efficiency will become maximum. So all this knowledge can be translated into parameters, which are engineering parameters in nature. Any confusion you have in this particular slide, because this will be necessary now for me to explain other things. Any question you have here? Anybody has any question in this slide? Quickly. Any question? Neeru, any question you have here?
No, sir.
Is it understandable? Is it clear?
Yes, sir.
Thank you. So let me move to the next slide. So in order to simplify this particular problem, what Randall did rather, about 100 years back. So he went for this, this is a free stream flow. And moment I'm introducing a surface, we are getting a boundary layer, right? And everything related to the engineering parameters are happening in the boundary layer, whereas free stream I can take care because it is not very difficult. Free streams are identical away from the boundary or the geometry. Free streams are identical, free streams are simple, but boundary layer has this sort of load structures, flow patterns, where I really need to worry about, where I really need to put my head in order to model these things in a very immaculate manner. So what Prandtl did, Prandtl said that, free stream we take separately, boundary layer we take separately, we model the boundary layer, and in that, we first, model the fluid flow, we model the heat transfer, we model the mass transfer, and then, with the free stream, I can connect this boundary layer, in order to get the engineering solutions, right? So what he did, he said that, a part that is laminar, which is a less Reynolds number, low inertia, a part that is turbulent where there is some sort of intermixing has started, whereas there is a turbulent at very high. This is a flat plate, the simplest geometry, where you have wake formation, and that boundary layer is called a turbulent boundary layer. Now we have to really model all these things in order to make sure that we really get the engineering information associated with this phenomenon, right? What is one very beautiful example apart from aircraft and all? Say suppose this swinging cricket ball, right? You saw this, this oval test, right? In the last day, suddenly India started, getting wickets, right? And then it was Virat Kohli who told what? That, Ravindra Jadeja was bowling on the rough. So, he could really roughen up, even if the ball was old, he could really make one side heavy. This was he told, if you look at the comments that he has made, that, while he bowled about 20 years on the rough, 20 overs on the rough, what happened, one side, both the sides got roughened and they were making, one side heavy with their sweat and all. And in that process, the ball started reversing and Jasprit Bumrah could get 2 wickets moment the ball started reversing. So what has happened there? It's exactly the same fluid mechanics that we are studying here. So say suppose this is a new ball, right? And you will find that the bowlers will angle this seam and then they will throw the ball right like this, right? There'll be an angle seam and they'll throw like that. So this is an experiment that has been done, that you just have a smoke, you have this the deuce ball, and then what you do, you flow the air. So in case of a conventional swing, what happens? Say you start shining on one of the sides, right? You don't shine both the sides, you shine only one side. So this is the smooth side where you have a creeping flow, and the other side you have a turbulent flow. Turbulent. This boundary layer becomes turbulent. The separation points is much nearer, whereas the separation point, because it is turbulent, it is towards the downstream. So in that process, when it is moving like this, this airflow, this is creating a. So if this is a boundary layer, if you have a turbulent boundary layer, whatever energy you have given, that has been expanded more here, whereas that energy is preserved here. So you have a pressure drop, lateral pressure drop in that direction. So this ball is going to go like this, which is the outswing. If you put the seam like that, it will become an inswing. So, based on the seam position and because of the seam, the boundary layer is created through the roughness of the seam only, right? The turbulence in the boundary layer is created. Now, this is happening at the velocity of, say, suppose, 120 to 135. Right, where you are trying to make this part as a creeping flow, a separation zone, whereas on the other part, you are trying to make it turbulent. Whereas for a reverse swing, you need a little bit of higher velocity. So suppose those who are bowling at 140 to 150 kilometers per hour, they get typically reverse swing. Now in that situation, your both sides are rough, but then with the polishing for 30 overs, what you have done, you have made one side is little bit more smooth than the other side. Right now, if you put the seam like that, what will happen since this is roughed up? So in this place, like the pressure will be less. In this place, the pressure will be small. Since both are turbulent boundary layer, you are forcing them at a very high velocity. What will happen with the same seam position? It will start going towards the other direction. Right, and then this will become a reverse swing. So you can see the laminar boundary layer, turbulent boundary layer has applications starting from car to aircraft to the swinging cricket balls to the tennis balls, okay, to the golf balls, okay, to the volleyballs, basketballs. Everywhere you will find their application in terms of very interesting. If you really understand that, you will find it very, very fascinating. Right now, who actually could figure out this part? This is the experiment. I have taken this from his paper, what he published. This is Reynolds himself, right? And this is his experimental setup. So you can really understand what is the size of this experimental setup. Why was it so big? Because he had to make a flow. He had to really make sure that, you understand that now for a laminar flow, you need some length at the entrance in order to make it fully developed, right? Now, say suppose if you have a very, very, very short pipe, what will happen? The flow may not become a fully developed flow, but it may remain a developing flow. So that's the reason why he created what he created. He created an experimental setup where the inlet is very, very long, and he ensured that the place that the probe he is putting, there the camera that he is putting, the image that he is taking, in that, it has enough entrance. It has developed a lot. And then it has no entrance effect by the time he's doing the experiment. So what is the experiment he's doing? He's flowing water into the pipe. He's making that the entrance effects are alleviated so that it's a very long pipe, the fully developed flow he has attained. And in the middle, what he did, he injected a dye. And that dye, what he saw, that when there is a critical Reynolds number, below a certain value of Reynolds number, this dye will just follow the path that is there in the fluid flow. If you have a pipe flow, if you just inject, it is just going to follow. So then he could conclude that it's a layer by layer flow. But if he is beyond a certain Reynolds number, so he may see that this dye will immediately mix downstream. That means, intermixing of layer are going to mix the whole thing. So this is the first invention which actually could demarcate the laminar flow to turbulent flow, right? And then what are the characteristics of turbulent flow? Number one is it is random. Okay, what is this? What are these options? Number one is random. It is three-dimensional. It has vorticity. That means there are recirculating zones, and then there is large Reynolds number, right? And then he said that there is a part, although it's a chaotic and fluctuating and random and 3D in nature, but you can really find a mean velocity, that is U bar I, and a fluctuating part, okay, over a period of time. So this is the first important decomposition. This is called the Reynolds decomposition, mean and fluctuation. Now you can think about how exactly one should average. The average can be of two types, ensemble average. What is an ensemble average? Suppose you are, suppose 90 students in the classroom, right? Now, if I really want to measure the average height, what I will do, I will go to individual student, and then I will measure the height, and then from there I will divide by the number of students. I'll get the average, right? This is called an ensemble average. Whereas there is another thing which is called the time average. So suppose I want to know what is your average height throughout your life. So what I need to do, I need to really note down at each and every age, what is your height, and from there I can get a kind of time average, right? So here what we are talking about is a kind of time average. This, if you really look at this fluctuation, what has been found out for most of the turbulent flow, which are not very random and chaotic in nature, this time variation of this U dot, if you just do it for a long duration time, that fluctuation is fluctuating velocity is zero, right? So first what is done, it has been defined by the mean and the fluctuating velocity. And then what is done, then you place this decomposition. So you know that this is initial notation for what? This is initial notation for our continuity equation. This is our initial notation for the Navier-Stokes equation. This is also called the Ocean's equation, right? Okay, where this is the local acceleration, this is the convective acceleration, this is the pressure drop, and the viscous term. Now question is that this is true for a laminar flow. So this is continuity and this is momentum, correct? Now, if you put Reynolds decomposition, if you put U mean and U fluctuation, okay, and P is P mean and P fluctuation. So Uj means you have basically 3 velocity components in a 3D, and then you have pressure, and then you replace them. So what happens? So you get what? First you get this is the equation that you get for the continuity, and this is the equation you get for what? This is the continuity for the mean flow, and this is the continuity for the fluctuating flow. This is one thing you get. Now second thing is what you do. You replace essentially you replace this U bar plus U dot in the convection term. So this is the convection term, right? So what you do, you replace it. So UI, Uj, Uxi, this is UI, Uj, you put U plus this, and then you separate out these 4 parts. You see slowly this fluctuating part is emerging that we take to previously. This is for j equal to 1, 2, 3 for all the 3 velocities. Now, if you do a time averaging of this, you end up getting an equation. So if you do a kind of time averaging of all these things, you end up getting an equation which is like this. So this is your average convective acceleration, and this is your fluctuating convective acceleration. Simply it is coming from the convection term, right? Now, so if you just add up all the average terms together, you will find that this is your average, and then you just remember that in case of this convection equation, the fluctuating time average equation, this becomes 0. So only average term sustains, and then other places also you put the fluctuating terms to be 0. So if you try the whole thing, so you will find that this is your time average mean velocity, this is your average convective term, right? This is your pressure term, and then this particular term which was coming previously here, this one that you take to the right hand side, Ui dash and Uj dash bar, that you keep with the viscosity term that you already have. So what do you mean by this? That these are called the AD viscosities, AD diffusivity. So what you do in turbulence, apart from the dynamic viscosity, which is the frictional loss, you say that because of this Vx and recirculations, you have additional stress term, right? Which you call that tau ij for the turbulence. What is this? This is tau ij for the laminar, right? This is tau ij for laminar flow, right? Whereas for turbulent, you define this particular component as the tau ij for the turbulence. So Niru, is it clear from where is it coming? Is it looking a little bit straightforward now?
Yes, sir.
So can you see it, how exactly it is happening? So if I just replace back the mean and fluctuating parts into the same momentum equation, what I have 2 additional terms coming, not rather 2, these are all 6 terms coming, right? So in a tau, we had read that, how is tau? What is tau laminar? How tau laminar looks like? The tau laminar looks like this is tau 1, 1, tau 1, 2, tau 2, 2, tau 2, 3, tau 3, 3, right? This is tau 2, 1, this is tau 1, 2, and this is tau 1, 3, and this is tau 3, 1, and this is tau 3, 2, right? We know that these two are equal. These two are equal, and tau 3, 2 and tau 2, 3. These two are equal, right? So essentially, how many stress terms are there in a Newtonian fluid? I have 6 stress terms, right? So this also you will find that there are 6 Reynolds stress terms. These are called Reynolds stresses. There are 6 Reynolds stress terms are there. Why? Because you are imagining a kind of symmetric matrix. Although it should be 9, but the diagonal components are equal. So now you have a continuity equation, you have a momentum equation where you have 2 additional terms like that, and then you need to know this fluctuating velocity. So how should you solve this? What will be your approach? How will you make sure that these are solved? So you add additional transport equations. So you need additional 6 equations in order to solve this problem. So you will find for a turbulent flow, 6 Reynolds stresses are added in order to really solve the problem, right? Is it clear now how the Reynolds stresses are appearing? So just to just to tell you, like, how these things are done, I have already forwarded you. I have already forwarded you this. There's an MIT open source, lecture note for this. The derivation I have already forwarded you, right? Please go through this derivation. There's a 2-pager I have already forwarded you. Just go through this derivation, how these Reynolds stresses they appear. Okay, and I have also shared with you. There's a turbulence lecture, by a professor, right? So this will also be very, very helpful for you. Like, and I have taken the content from there only, right? So you can really follow the entire derivation is given, like, how they are coming together, and then how the Reynolds stresses are coming, and then how the Reynolds stress equations are solved in order to really model the turbulent flow, right? So could I really clear up what is this fluctuating part, or what is this mean part, and then what is this turbulent flow, and then how this tau turbulence is coming out to be minus of rho u dash v dash, and then the mean of that. Is that clear? Yes. Have you understood? Any question is there? Quickly. Yes, no. Any question you have? Great. So since you do not have any questions, so let us progress on the part. Then now, say for a simple laminar flow, what should we do? Okay. So as we were discussing, that we take a flat plate, we take a boundary layer. In that we consider a differential area, and in that differential area, what I do first mass balance. So density kg per meter cube, u dy, and one is my perpendicular direction, right? So in that, this is the mass that is coming in through this phase, and then if I do a Taylor series expansion on this dx, this is the mass that is going out. So this is the mass that is coming in through this phase, and this is the mass that is going out. So if I do a balance, last class we saw this is giving me the continuity equation, right? And you can understand now this is more of a laminar flow because I am not decomposing them into u bar and u dash that will come in the turbulent domain, right? And for momentum, you just multiply u with u and v with v. Okay. Here you are not multiplying v with vy because you are only considering x directional flow. So you are also multiplying u with v only in order to get the simplified momentum balance equation for this. And then you can see that you get so this is called the Ocean's equation. By the way, when the time component is there, that is not the Ocean's equation. When the time is not there, the steady state Navier-Stokes equations are called the Ocean's equations, right? So these are the Ocean's equations. So momentum balance you get from here, right? And then you play a trick for the boundary layer. Okay. So what is the trick? Let us understand today the geometry. We'll perform the derivation tomorrow. So first, what I do, I take a flat plate, and I assume that there is a developing boundary layer whose thickness is delta, and this delta is changing with respect to the space. But then what I do, I create a control volume whose height is h, and then the width is dx. This h is such that it is much larger than delta. So a part of it is into the free stream, and a part of it into the boundary layer. Now in that boundary layer, I assume a differential element dy, and I try and see in that how the mass balance and momentum balance takes place. So in this particular system, I have 1A2. This is my domain of operation. So initially, I take all the parameters to 1A2, and then I try and do a kind of Newton's second law here. And then I try and see how exactly I can reduce the entire set of knowledge to this boundary layer that is called the delta, right? So for that, what should I do? Very quickly. So you know that, say suppose 0 to h. So plane 1 through plane 1, what is the mass coming? So 0 to h, rho u dy. We did that. Rho u dy is what was coming in through 1, right? But then for 0 to h, I do a kind of integration. This is the total mass flow through plane 1. So total mass through to plane 2, it is just a Taylor series expansion I have done. and then that I add to this, right? So this is the total mass balance. Now momentum through plane 1 is this rho u square. Momentum plane 2 again, the same thing, just Taylor series expansion of these two. Now once I am done with that, then what I do, if u infinity is the free stream velocity, what I try to judge, the mass flow carries with it a momentum. Say suppose if something is flowing, right? If u infinity is the free stream velocity, so the mass flow carries with it a momentum in the x direction. This mass flow, whatever is the mass flow I have achieved here, what momentum it is carrying? It is dx. So suppose this is the mass flow. So d dx of 0 to h rho u dy dx. What is the momentum it is carrying? I multiply this with u infinity. So in this box, because of the boundary layer, I can really force a mass and momentum balance. And because of the free stream also, I can see the total amount of mass carrying and momentum carrying, right? Now what I get, if I subtract this momentum from the momentum that is there, so net momentum comes out to be what? Net momentum is whatever I have assumed in the whole thing minus net momentum for what? Net momentum for the control volume that I have decided, right? This is dy and this is dx. So once I have done for the total with the mass flow, and once I have done for the total with the momentum. From the mass flow with u infinity, I have got one momentum, and from 0 to h, I have got another momentum, and the difference between these two is the one that is happening in my dy and dx, and that's what. So this part is subtracted from this part in order to get this, right? And then I use a vector identity. So d of n phi equal to n d phi minus phi dn. So I use this in order to really see that, d of n phi means, so d dx of u infinity 0 is rho u dy dx. If you do that, you will see that, u infinity can come out d dx of 0 u rho u dy, plus then, if you take this one out, du infinity by dx, 0 u dx, right? So essentially, I'm using this vector identity to rearrange this part to make sure that, u infinity d dx of 0 to h rho u dy dx is equal to something like this. And this is the genius of the Ludwig Prandtl. This is the onset of the concept called boundary layer, under which, the entire theory and concepts of boundary layer that flourish later on. Okay, so since it is 1 p.m. I stop here. I will start the discussion tomorrow from here itself, and we'll try to finish this chapter, because not much is remaining after this. Once we are through with the derivation of this boundary layer, then things are pretty much straightforward, and we'll try to finish as much as we can. And this will be up to this particular lecture. There will be the syllabus for the exam will be up to this particular lecture. Okay, yeah. Any question you have up to this point? Anybody has any question up to this point?
Sir, when will we get the marks for tutorial?
Is it? I think that they are on the way. So Vinod, can we share the marks? Are we in a position to share the marks?
Sir, it will take some time. So once we will finish it, I'll let them know.
Maybe after the mid-sem exam, we'll communicate the entire details of marks until I think of 4th tutorial. You will get just after the exam. Okay. Yeah. Any other question you have? Okay. So if you do not have question, we'll